This is session 2 of Unit 3, session 2, independent event. What do we look forward to? By the end of this session, we should be able to define independence, use techniques of conditional probability to explain independence, differentiate between conditional probability and independence, and then calculate probability involving independence event in real-life situations. So let's see, how do you define independent event? Independent events. Two events are said to be independent if knowing one event occur doesn't change the probability of the other event, or the occurrence of one event does not affect the occurrence or non-occurrence of the other event. So in a simple sentence, what it means is that two events can occur together. The occurrence of one particular event will not affect the occurrence or non-occurrence of the other event. And if it happens so, then we say that those events are independent. So if you have individual probability of event E, given that F has already occurred, as we learned from the conditional probability, then we're going to have probability of E given F, and that is equal to probability of E intersection F all of probability of F. It is always divided by the probability that was given or that has already occurred, because that's what we know. And this probability that we know should not be equal to 0. Now, by way of cross multiplication rule, we will have probability of E intersection F being equal to probability of E given F multiplied by probability of F. So we call this the general multiplication law of probability. Definition. We are still on independent event. So two events, say E and F, are called independent two events. If and only if, that is, probability of E intersection F could be written as probability of E times probability of F. So what it means is that the two events can occur together without the occurrence of one affecting the occurrence or non-occurrence of the other one. Now, if that is the case, then we said that those two events are independent, as you can see. Now, what it will mean also is that if probability of E intersection F is equal to probability of E times probability of F, then E and F are independent events. On the other way around, if E and F are independent events, then the same rule holds, that probability of E intersection F is equal to probability of E times probability of F. Maybe an example will do. Let's pick an example. Example 1. Using the given probability to determine whether event A and B are independent events. So we are just to check whether those two events given are independent or not. So in the A part, we give probability of A being 1/3 and probability of B being 1/5, and the probability of A intersection B equaling 1/15, and the values of the B is also given a probability of A equal to 0.3, probability of B equal to 0.7, and probability of A intersection B equal to 0.14. Now solution. So to check whether A and B are independent, and we said the rule earlier that if two events, let's say A and B, is independent, then probability of A multiplying probability of B, if that same is equal to probability of A intersection B, then the two events are said to be independent. So with the A part of our question, probability of A is 1/3, the probability of B is 1/5. So multiplying those two probabilities together is equal to 1/15. And comparing that to A intersection being given in the question, that is also 1/15. So since probability of A times probability of B equal probability of A intersection B, which is equal to 1/15, then we can confidently and conclusively say that the two events, that's event A and B, are independent. Would you like to try for the B part of the question? Would it be independent or not? Well, multiplying the two probabilities as the A and the B, that's 0.3 and a 0.7, you have 0.21. But then probability of A intersection B given the question is 0.14, and we can all see that 0.21 is not the same as 0.14. Hence, probability of A intersection B is not equal to probability of A times probability of B. So this simply follows that those two events, that's event A and event B, are not independent. Example 2. A fair die and a fair coin are tossed at the same time. What's the probability that the die show a 2 and the coin shows a head? So these two events will be classified as independent. Whatever outcome we will have on the die will not affect whatever outcome we have in the toss of the coin. Yes, you agree. And then these two events are independent. Now you should find probability that the die shows a 2 and the coin shows a head. Now if you let A be the event that the die show a 2, how many 2 do you have on a die? A single die, that's only 1. Out of how many numbers? Out of 6. 1, 2, up to 6. So the probability of A will now be equal to 1 over 6. Agreed? Yes. And then, if the probability of event B be the coin that shows a head. You know, in the toss of a coin, you have only 2 sides, a head and a tail. So the probability of a head will be 1 out of the 2 results, or the 2 possible results. So the probability of B equal 1 over 2. Then we have to find the probability of a die showing a 2 and a coin. That end in a probability alone suggests intersection. So you have found intersection A, probability of A intersection what? B. That is what the question asks. You should find probability of A intersection B. So that will give us probability of A times probability of B by the rule of independence. And that gives us 1 over 6 times 1 over 2, giving us 1 over 12. Remark, what it means is that this could be extended to 3 events. So we are not limited to only 2 events. It could be extended to 3 events. That's the probability of A intersection B intersection C could be equal to probability of A times B times C. Well, let's work one example on that. Example 3. A school survey found out that 9 out of 10 students like rice. If 3 students are chosen at random with replacement, what is the probability that they all like rice? So if the probability of a student liking rice or that like rice is 9 out of 10, that will be equal to 9 over 10. Now we are talking about we selecting 3 students and with replacement. So if it is replacement, the probability of each event remains the same throughout, because once we've done the selection and we replace back, we will still have the same result if you go back to make the same selection again. So that will give us the first selection will be 9 over 10, the second will be 9 over 10, the third will be 9 over 10. That will be probability of the first one, let's say being A, second one being B, and the third one being C. They're all 9 over 10. And that will give us 729 over 1000.